tool, which is used for observing and analyzing inter-AS connectivity.
Hi, everybody. So my name is Ricardo Oliveira. I'm from UCLA, and I'm here to present this tool to the network operators, to collect some feedback from you, and see if there's new features we can add to the tool to make it more useful to you, because that's the end goal. So this is a joint work by all these people from UCLA. So we start working on this after looking some messages in a NOC mailing list. For instance, this is a message that appeared on July 8, 2007, asking if someone leaked some routes from Yahoo. There's some other messages asking if Cogent really depeer Limelight, V5 and Layer. And more recently, this message about the telecogent accident that was discussed in this morning by Renesys people. So basically, there's network operators see that there's a problem. They think there's a problem going on, and they send this message to NANOC mailing list in the hope that someone might shed some light on the incident. And the problem is that so far, even though this information is available, the routing information is available from public sources, such as route views or RIPE. So far, there's no systematic way to collect this information in a systematic database and show this information, so that everybody can use this. This is one of the other objectives of this tool, Cyclops. So ISPs know that their connectivity, they know the grantors of their connectivity, they know who their customers are, who the peers are, providers, and so on. And the public view, which is the connectivity extracted from the public sources, routing tables such as route views, RIPE, and so on, captures a fraction of these grantors. And may actually capture more that ISPs were not expecting. For instance, there might be cases where, in this example, you have ISP X that announces a prefix P here. And suppose that there's this other ISP Y that wants to hijack the prefix P. But by announcing it to another IS Z. But in this case, Z does some checking on the Internet Routing Registry, for instance, and it can actually check the mappings between the prefix and the origin AS. So the only way Y has to trick Z is to basically append the true origin X to the announcement. So when Z receives the information, it has no way to tell if it's really a true route or not. So the Cyclops concept is pretty simple. At the highest level, we have this view here. We have the central node, which is the high of what we call the high of the Cyclops, therefore the name. And incident to the eye, we have a set of changes. The green links, the green edges here correspond to new peerings, and the red edges correspond to depeerings at a certain instant of time. And the way we show this data, we use 3 different flavors, if you will, for Cyclops. The first one is the most basic one, is just show the raw data. Basically we show for each day the connectivity of each ISP. I'm going to go over more detail over this information later on, just to give you an idea of the 3 components. Second one is the web interface. The web interface is a more elaborate way of displaying the raw data. Users can use a series of filters, data filters, AS numbers, and so on, relationship types to filter down the information they're interested in. And finally, the last one is the visualizer, which gives a graphical perspective of the changes at a specific point in time and enables the correlation between different events. And I'm going to go over this later on. So Cyclops in a nutshell. So the features enabled by Cyclops, as I mentioned, number 1 is fault detection, detecting these BGP misconfigurations, false link attacks, route leakages, and so on. Also provides a quick view of the the connectivity of certain ASs. This might be useful for also for research purposes, protocol studies, and so on. The other one is enables detection of anomalies, anomalies depeerings, massive depeerings, and so on. And finally, the event correlation. So this is kind of a diagram block of the architecture. So everything starts here in the bottom with the BGP data. This BGP data undergoes a preprocessing stage where we extract all the S links from the S paths, and we stamp each link with timestamps, initial timestamp, first seen and last seen. And this information is actually available in the form of topology and weight files. So the weight files are basically the number of routes carried on each link. This information is also passed to another block, the S relationship inference and AS classification block. So we have ways of determining if links are provider, customer, peer-to-peer, and so on. And the S classifications, right now we are using a very coarse classification. We have basically 4 types: tier 1s, large ISPs, smaller ISPs, and stubs. So all this information is entered in the Cyclops database, which is the central part of the system. And this information is input to the 3 components that I just mentioned: visualizer, web interface, raw data. So the raw data, the usefulness of the raw data is to do post-processing at the ISP side. And one feature that we are currently working on is the alarm generation. And actually, I would like to hear some feedback from you to see what alarms can be triggered, what parameters to look at, and so on. So right now, about the frequency that we update the database, we're doing it in a daily basis. So every day we run this script to collect all to clean all the S-links information. But this might not be enough for some cases where you need a faster response, for case of hijacks, for instance. So we are actually planning to move this to a close to real-time system using this infrastructure from CSU called BGP-Mon. So this is also part of your future work. Okay, so now going into more detail into the raw data, which is the first, the very basic information that you can download from Cyclops and website. So the link is up there. Anybody can download it. The way we organize data is that we have a directory, and the digit on the directory is the last digit on the AS number. So for instance, in this case, UCLA 52, you should look for directory number 2. And then inside directory, you have a name with the AS number. So the information in the file, in these files, first you have this AS number of the neighbor. In this case, the neighbor of UCLA, 2153 S number. Then you have the name of the S number, California State University Network. Then you have the type of neighbor. In this case, it's a large ASP. You have the relationship type. You have the degree, the time the link was first seen in BGP, the time the link was last seen. And lastly, you have the field, which is the last BGP message seen on the S link. So the goal of including this information, the last BGP message, is to give some hints for someone that is troubleshooting some accident, some leakage, and so on. You can't just look at the last BGP message and see which prefix was being announced and which were the AS passes in question. So ISPs, by processing this file, they can look for suspicious cases of neighbors that were not supposed to be there. So they can use the scripting tool at their side to do this. So the second component I'm going to talk about is web interface. This is also available in the website, Cyclops website. So these allow users to have a quick view of the snapshot and connectivity, who connects to whom. So there are basically 2 modes of connectivity. You have the change-only mode and the connectivity mode. Change-only, it only displays changes in connectivity, new peerings and depeerings. And the connectivity is basically the snapshot. So this is how it looks like. The most important field is this one, is the S number, which is the eye of Cyclops. Then you have the start date and end date. In this case, I'm looking at change only mode. So this will display changes in connectivity between these dates here, within this interval, between the start date and end date. Then you can also do a further filtering, filter entries by node degree, type, relationship type if you only want to see peers or customers. And this is another interesting thing we can do with the web interface. So each column can be sortable. In this case, I'm sorting the lifetime column. So the lifetime is the time in days between the first appearance of the link and the last appearance. So a lifetime of 0 pretty much is an indication of trouble. It means that the S-link appear and disappear within the same day. So it can either mean there was some misconfiguration, or most likely, or someone, some malicious attack. So this needs to be looked at. The other information we display is the weight information for each link. So the weight is basically the number of routes carried in each link. And compute the weight, we basically do an average over about 100 monitors with full tables. And we keep track of the change over time. So we show the average weight in this column here. And then we show the difference between the last value we saw and the average. So if this difference is significant, it means that there were lots of routes changing from this link to another link, or disappearing or appearing. So this probably needs to be looked at also. And this is the kind of thing I also want to get your feedback about, if this is really a useful feature that you might think might be needed. And finally, the visualizer. So the visualizer has a different set of notations to refer to different types of nodes and different events, peerings and depeerings. In the center, you have a blue node, which is the eye of Cyclops. In this case, is Quest AS209. And then you have a set of red nodes, which means that are nodes that disappear, AS numbers that are no longer visible. And red edges are depeerings, green edges, new peerings. And here below you have the time slider. So you can control which is the time you are interested in observing the topology and so on. And in the right side you have the set of filters, which pretty much are the same of the web interface. And you have this new this display here of the activity plot, which I'm going to talk about in next slide, next 2 slides. So this is a summary of the notations we use. So we identify different nodes within different notations. You have stub, transit, tier 1, and so on. So this actually might not be useful for large dimension graphs, because it becomes too clumsy. You have too many nodes in display and you cannot extract anything from it. But once you have these filters in action, it becomes more readable, the graph. So the main goals of Visualizer is to do event correlation. So correlate on visually peerings or depeerings that apparently are not correlated. And also the activity plot. It helps search for anomalous events. So this is an example of the activity plot. So the activity plot is pretty simple. Basically it shows on 7-day bins peerings and depeerings that occur over time. In this case, we are looking at data from 2004 to 2008, so it's a period of almost 4 years. And the red edges, the red bars correspond to depeerings, and the positive green bars correspond to new peerings. And there's also this sliding bar here, the gray bar here, that should that you can slide, and you can zoom in on a specific time interval, which will going to be reflected in the main layout. So these again the filters that I already talked about. So now let's start with case studies. Case study number 1, Google route leakage. So this happened in July 19, 2006. So we started looking at the activity plot, and we noticed there was this specific period there with an anomalous number of peerings and depeerings occurring pretty much on the same time interval. So what we did was we zoom in on this interval, and we got this graph here. And in this graph, you have in the middle, which is the eye of Cyclops is the S number of one of the S numbers of Google, and you see a bunch of incident depeerings with a lifetime of 0. So the lifetime is indicated in the labels on the edges. So this means these links disappear and appear within the same day. And this was actually later confirmed by Google that these actually correspond to a route leakage. So this was second case I have is about Yahoo outage that was talk about July 6, 2007, and there was a discussion on Nanog mailing list about this. So some points of the network stopped reaching Yahoo, and people were wondering what was going on. Nobody had a very specific clue, except maybe for Yahoo, sorry, or maybe Google also. So in this case, what we did, we centered the main layout in the one of Yahoo's AS numbers, 10310, and we noticed there was this depeering here with a lifetime of 0. So we expanded the neighbor that disappeared, this AS number 9318. And what we noticed is that a similar pattern of what I just shown in the Google case, this set of incident links with a lifetime of 0. So all these links were pointing to this guy, 9318. So it turns out that apparently there was a route leakage by this guy to start announcing Yahoo routes to neighbors it should not announce to, and traffic to Yahoo was compromised from some vantage points. And this analysis was actually confirmed in this other website, this independent analysis on this website here below. Okay, so the last case I have is about the Cogent depeerings. So there was this question if Cogent really depeered Limelight, WV5, and N layer. So we just look into the graph change of Cogent. So it's this AS number here in the middle, the blue node, 174. And we start looking if we saw this the Limelight, the S numbers in questions in the graph. So we saw Limelight, WV5, but we didn't see N layer. So apparently Cogent did not depeer N layer, and this was actually confirmed later on by some posts on Nanog. Okay, so future work. As I mentioned, we are working on this idea of having a subscriber-publisher system with alarms. In case that ISPs are interested in receiving alarms whenever there's a link with a very short lifetime, or in case there's a significant change in link weight, and so on. So these are parameters I wanted to get some feedback from you guys. And also, as part of future work, is to make this close to real time, as I mentioned. So I'm very interested in getting some feedback from ISPs. You can check the tool at his website, cyclopscs.ucla.edu. The web interface should be pretty easy to use. For the visualizer, it's a Java application, basically, so you need to download the code and run it in your laptop. But I want to hear some feedback. In what way did Cyclops help you, and what things do you like to be added to Cyclops or change it? Please contact me. This is additional information. We have this topology database website here in the bottom, IRL topology page. The raw data, anybody can download it. You can set up a cron script to download data on a daily basis and do this comparison of the connectivity of the R side. There's also the mailing list, and I think that's about it. So if you have any questions. By the way, tomorrow there's going to be a tools buff, and I'm going to do a demo of Cyclops, so I'm going to leave there for tomorrow. Leave that for tomorrow. Okay. Thanks.
Okay, thank you, Ricardo. We've got time for some questions. Any questions?
Hi, it's John Christoph from Newstar. Just a quick question. I apologize for coming in about halfway, so you may have covered this already, but the raw data really interests me, so if it's possible, if you didn't already make available those tools to create that, I'd be interested in creating that raw data. And the second thing is, I'm sorry, I missed the beginning of the presentation. I assume you're a graduate student, a Ph.D. student. Sometimes these projects have a tendency to die after a period of 6 months when you graduate, so if there's some plan to keep this going, that would be great, of course.
Okay, thanks. And the plan, there's a plan, but it's just starting the plan.
I just want to comment, I'm not a student. My project is not going to die.
You're a postdoc.
Yeah, if I get a faculty job and become a professor, then I have the job for life, then I won't die. Until I die.
Okay, good to know.
Okay, great. Thank you.